A rare cosmological event is perhaps one of the most appropriate ways to describe what is building to a crescendo here at Earth. In this video, we will see how one rare cosmological event relates to another in the examination of the third way to tilt the world. To review, in our series so far, which aims to shorten the previous dozens of videos on this topic, we have gone over the cycle, the evidence, the mechanisms, where we are in the cycle right now. The advanced catastrophism videos were about the tilting of the Earth in the cyclical catastrophe, and at the end is the full movie from 2019 on this topic. We have reviewed two ways it is possible for the Earth to turn over, and to examine the third we must begin with cosmic jets. How do they form? What causes their outbursting from the north and south poles? And what can we learn from it? The jets are the product of interaction. You won't see them in old galaxies depleted of gas. If not a constant stream of material feeding a constant jet, temporary ones can be seen around compact stellar objects and larger, even if there is still some ambiguity about the central sphere magnets themselves. We see the same from some stars that can efficiently outflow the incoming material. Some can be maintained for the lifetimes of those stars provided they have the fuel, but you can also find those temporary jets, especially at the baby stars. And of course, many end their lives in jet-like fashion with the polar blast, even if not collimated. Here, we are looking at a cosmic jet of microscopic size inside of Muscovite mica. It is actually called a rare cosmological event because they can't explain its appearance and they can't imagine what kind of phenomenon would have caused it, and especially because there was no way it was a cosmic ray impact event. It was a residual, distributed input of positive charge that overloaded the crystal. The energy outside was still too great to discharge outward, and so it explosively deformed inside. For the supernova versions of the jet feature, this inside-out boom isn't far off. Other crystals could contain these, but are super hard to find, and Muscovite is probably the best place to find them due to its odd electrical structure. In fact, only a few of these rare cosmological events have ever been found. None explained, other than this rare event they can't yet conceive. Well, what if the entire crystal was bathed in the charge? Forget the cosmic ray single hits, can't be that due to the lack of fanning. It's a buildup above, below, and all around, engulfing the crystal until it crosses a threshold and discharges within for lack of a better pathway outward due to presumably still higher charge differential. Indeed, not one particle, but many, uncountable sums in unimaginable magnetic field scenarios bathing the entire planet in the energy and reversed magnetic system of the galaxy. So forget the crystal for a second. What about the entire Earth? Earth is a capacitor, and we've seen the conductivity traceable down through the mantle to the core, especially with the extra conductive internal skeleton, the LLSVPs. And by the way, notice how they come out opposite sides of the core region, almost like the cosmic jet outblasting from the overcharging. Of course, it's not at the north and south poles, but if it were, its weight would drag the planet over and put them spinning at the equator due to centrifugal force. This is actually what stymied Einstein and many others. The world tilts, but where's the imbalance? If the solar micronova overcharges the core beyond a threshold, the current LLSVPs break down, the energy outside the capacitor is still high or even growing, and there will be no outward discharge possible, the system could discharge within, in the north-south directions. This would then turn the Earth over 90 degrees every 12,000-year energetic surge and galactic magnetic reversal. Folks, do I like this better than the other two ways we showed the world able to turn over? Unlocking the crust and the intermediate axis asymmetry? Hard to say. I can say that given the magnitude of the event about to unfold, any or multiple of the three could be in play. I'll see you in the morning for the daily update as we await the next rare cosmological event. Be safe, everyone. After our last special video about catastrophe evidence and the galactic trigger at the two closest stars to our system in the direction of the galactic center, there are basically two questions about the galactic current sheet. First, what is the galactic current sheet? And two, can we tell how long until it gets here based on those two closest star events? Well, the galactic current sheet and what it is, and how it triggers the solar micronova, is largely covered in our existing 23-part series, in the full movie, and especially in the Nova Triggers video, all of which are linked below. But perhaps a bit more is needed here, and we can use the solar system, the sun's current sheet, to learn about the scaled-up version at the galaxy. Keep in mind that the sun and galaxy rotate the opposite ways as we perceive north, so the curve of the galaxy goes the other way, but the further you get out, the less the curve actually seems to matter. From seeing out to Mars to seeing out to Jupiter, we can see that the bend halts at the radial motion, the rotational flow ceases, and a more concentric circle pattern is formed from the spiral. Well, galaxies are like this too, especially barred spirals like our own, where you can see the outward jut of the spiral towards the inside of the galaxy, then bend out to concentricity. And that is exactly what ends up happening once you get out into the solar system at Saturn, Uranus, Neptune, etc. While Mercury likely sees the sheet moving across it from the sun's perspective, rotationally, the outer planets see the sheet coming right at them. This is the best existing visualization of the sun's current sheet. In the solar system, it is mostly an ion density change and reversal of the solar wind magnetic field. But in the galaxy, the sheet contains the electrified particles and the galactic field reversal, but also the dust and gases caught in the front of the wavy sheet or attracted to it like a static duster in your home. As described in that Nova Triggers movie, it's the kind of thing that brings two separate ways to get a nova from a star, let alone a superflare, and it brings them at the same time. And so, with the sun at around the Saturn or Uranus-like distance from the center of the galaxy, if you can translate it that way, it means we are likely seeing the concentric waves basically emanating out from the center of the galaxy right at the sun, a radial outflow, not rotational, one wave after another. And so let's take what we know. These are the detection dates and light-year equated real flare years of the outbursts. I didn't include Barnard's in that last video, figured you could handle it. And when we remember that we are looking at stars that are 6 and 4 light years away, the 1992 to 2012 jump in occurrence means the wave triggered stars 2 light years apart, 20 years apart, which would mean that the 4 light years between Proxima Centauri and our star would be eclipsed in 40 years from 2012, or it would occur in around 2052. Nice and easy, right? Well, if you simplify the situation, yes, it is that easy. But here's why it might not be so easy in reality. This graphic we showed of the nearest stars is not exactly at scale, but pretend the center of the galaxy is way, way, way off the screen to the top, and indeed, Centauri is slightly off our view to the right and Barnard is slightly off our view to the left. If they were in a perfect line straight ahead, you could use that 6 and 4 light years, but this is a bit more trigonometry, and that's problem number 1. Problem number 2, no matter how far out you get in the spiral, it is never going to be perfectly concentric. The spirals do keep going out, and that means there will be a slight bend, if not the slightest of rotational flavors still lingering on the tongue of that sheet or wave. It is truly a shame that the only good animation of this galactic sheet field traces using the opposite spiral motion of the Milky Way. The correct one is at the bottom left. And so just pretend that those lines going out bend the other way, and indeed probably have to pretend they bend a lot more, like the sun's field. And this wasn't exactly the focus of the animation, and so it wasn't a key detail in their design. But in essence, the wave might come down at this image right horizontally. It might be angled slightly or curved slightly, even to the point where it was getting Barnard and Proxima at the same time. Just picture the correct bend. It's certainly possible. That's problem 2. We don't know the character of the sheet or superwave, or even which it is in this case. And that idea that the sheet could bend, and, in theory, could have been surrounding both those nearest stars at the same time, drives problem number 3, and it's the answer to the question of why then would there have been a 20-year difference in flaring between Barnard's star and Proxima Centauri if indeed they could have gotten hit at the same time. Well, the answer is that every star is going to be triggered differently. We briefly touched on this in the last video, but now think about it a little more. Some might just have a brightness change, some will flare, some will nova, some give off gamma rays, and something tells me that not only do each of those take different triggering times, but those times vary from star to star. It's not like we've got glowing plasma twins out there everywhere. They are, by and large, far more different than human to human, so consider that. Barnard, which had never flared before, maybe just needed a little push. The astrosphere around the flare star Proxima would indeed have taken much more to overcome. Maybe that's an explanation for its delay. And indeed, those star magnetic shields matter too. You ask how long before the sheet arrives. Well, who says it isn't here already? Who says it isn't a 100-year-long process going through it? Earth spends a couple hours in the sun's sheet every 2 weeks. So scale up a couple hours in 2 weeks to maybe 100 years every 12,000 years for the galactic current sheet cycle. Doesn't really sound so crazy. Certainly less crazy than it hitting in one day and being gone. It may have been affecting both Barnard and Proxima for years before we saw anything. And now, let's add to all of those facts the fact that our changes in the solar system have already begun. And remember, Proxima was a known flare star. It's now routinely flaring 10 times higher, with that one super flare being 10 times higher still. Now look at the Sun over the last century compared to most of the last 12,000 years prior. Since the last great magnetic excursion of Earth, the Sun has not done anything like it just did last century. Well, is that our Sun's version of 10 times higher activity before it releases one 10 times higher still? And furthermore, does it matter that Barnard's star is moving perpendicular to us while Centauri moves directly away? Does a star's proper motion, with, against, or sideways to the sheet make a difference in those triggering times? Are you starting to see how many moving parts are here? FYI, it has indeed been my position that the planets are changing due to the solar system-wide shift, which may be galactic after all. At this point, we are being affected already, likely in the sheet already, or taking the edge of the wave. So it may be 2052, something my children and perhaps even I would see. But it also could be much, much sooner. That's why, without anything remotely resembling fear, we have to keep our eyes open. I'll see you in the morning. Be safe, everyone. Good evening, folks. This video is both a reminder of what we need to watch for as Earth's catastrophe cycle is unfolding, and identifying the signs we've said to watch for in the past. With this morning's reminder about the activation of nearby stars, it naturally spawns the questions about using them to try to time the galactic current sheet impact on the solar system. But evidence suggests it's a long-term event, likely began here in 1859, and every star is different, requiring a different time to activate and a different form of that outburst. We have also gone over how it would be much easier to track this disaster if we continued to get updates on Earth's magnetic field strength. We got acceleration points and numbers on the field strength loss until 2015. We went from 5% lost per century to 5% per decade, and we have no idea of how things are moving after the 2017 acceleration. And I'm not fully confident they'll update this fervently, if at all. But we are not left in the dark. Two critical items we said to watch in our disaster book are showing up this year very solidly. This is in section 6.4, appropriately about the best way to judge the timeline, given that we are not getting updates on Earth's field and we can't really rely on those extrasolar timeline markers. The first thing we can watch is lightning. This is something that should be seen surging in number, power, and perhaps even form. A considerable portion of our solar terrestrial physics textbook, Weatherman's Guide to the Sun, is about how lightning is triggered by cosmic rays and solar storms, and the weakening magnetic field should whisper that secret to the lightning, who will promptly snitch on the overloaded capacitor of the planetary electrodynamics. Our field is weakening, we're juicing up more and more. We've recently learned that the Arctic is shattering their lightning records. Many want to blame global warming, but the northern polar cusp is where solar energetic particles prefer to enter, and we would expect this atmospheric electricity effect there with Earth's weakening magnetic field. The global warming explanation doesn't work so well for the new mountaintop energetic pulses, a new form of upward lightning just identified, and in case you are wondering, it is utterly absurd that they've identified two new types of lightning in 1 year. And thunder snow? No. No global warming at work in the cloud electrodynamics there. Record lightning? Two new forms. That's about exactly what we've said to watch for as the field continues tanking on us here in the catastrophe cycle. But right after that in the book is found the second critical thing for us to be monitoring: space weather. One of our most popular presentations of the previous decade was an examination of the 2015 solar storms, which nearly had major global effects, but were caused by puny space weather. We had wondered if it was a sign of the weakening field, and a similar event is known to you space weather peer-reviewed literature experts out there from August 2018, the unexpected geomagnetic storm. And so far, we've already seen two overreactive dings to the planet just this year. Solar Cycle 25 is ramping up, and we can finally look at more than just the lightning. A minor CME produced a strong storm earlier this year, and a very minor CME recently grazingly gave us a love tap, and the field spazzed out for most of this past Monday. What we're watching for is space weather having a greater effect than it should be. Folks, it is indeed impossible to use the galactic markers, and if the officials don't update the field loss or loss rate, we are left seeking other means to run the timeline. Lightning and space weather, it's a great 1-2 punch, especially because before the greatest solar flash, before the magnetic excursion finalizes, the weakened field will likely leave us vulnerable to a space weather event and those terrestrial storms. The best way to judge how far we're tracking down the line is the same thing that provides the most imminent natural threat to modern condition. For this, we have about a 1 in 4 chance of taking such a solar storm this sunspot cycle, would likely be before 2027, and by the 2030s, the field should be down to an almost untenable state. That's why we need to be as vigilant as the sun is dependable to rise each morning. Speaking of which, I'll see you tomorrow for the daily update. Be safe, everyone. Good evening, folks. I often get similar questions about the tilt of Earth in the cyclical disaster. They're ones I don't usually cover in detail. They're things like, why is there evidence of the magnetic poles in their positions for millions of years if the Earth tilts? Why do ancient star charts show the stars as they are now, or the monoliths still line up perfectly with the stars if the Earth tilts? Why is some Antarctic ice over 1 million years old if it goes to the equator every other cycle? Well, the first two were easy, as we have gone over some of them. The Pentagon papers taken by Major White support the story of numerous others and the modern observations, and they suggest the poles go back and forth, putting them in the same places repeatedly. This is why there is indeed expected to be that evidence over long periods. As for the star charts and monoliths with astronomical significance, I'm pretty sure most of those are less than 6,000 years old. All are less than 12,000 years old. They are all from after the last catastrophe and tilt, so yeah, they better be the same. But the one about the million-year-old Antarctic ice, That one is a bit harder, and I bet some of you were wondering about the ice that goes to the equator from the poles and what happens to it. For this question, about a million-year-old Antarctic ice, we need to address three things: the dating, the equatorial glaciers that exist today, and the uniqueness of the Holocene, the period we're in now. So first, if you recall, they once thought Greenland ice was over 1 million years old as well, and then they found evidence that the entire thing was ice-free in the last 100,000 years. They make a lot of assumptions about Antarctica, and on top of those, there is a problem with the isotopes they use to date ice as well. We've spent a great deal of time going over the dozens of studies like this one, which does happen to be my favorite, where they thought the ice in Tibet was over 500,000 years old, but now say the upper limit may be less than 20,000 years old. Million-year-old ice in Antarctica? I wouldn't be so sure about that. But hey, let's forget what we just said and play devil's advocate. Let's presume they are correct. Yes, you can still move the current polar positions to the equator every other cycle, and no, there is virtually no chance that they're going to melt away. Here is where today's low latitude, the current tropical glaciers reveal, and the heat of the last 12,000 years tends to trick our imagination. When we see the equatorial glaciers that exist today, we must realize that those are still there after 12,000 years in the tropics, and that is with the Holocene, the name for our current hot interglacial, being way hotter than previous 12,000 year cycles, with the last 10 of them being within the glacial period of the approximately 100,000 year cycle. The previous interglacial was over 120,000 years ago. Well, what if this wasn't a hot interglacial that we were in right now? What if this was a cycle 50,000 years ago? How much ice would be left at the equator after 12,000 years at that point if the world was in a glacial period? I'd wager there'd be much more than just a few remaining tropical glaciers. There would still be enough left to make you look at Antarctica and Greenland and say, yeah, 12,000 years is nowhere near enough to melt all of that, especially if you take 3 to 6 degrees off the planet. By the way, the areas with tropical glaciers will be heading to the poles once again, just like last cycle when they accumulated the ice that is still there today. And so yes, there may indeed be ancient ice at Antarctica, and it doesn't change the story one bit. The heat of the interglacial is tricking us into thinking that all of Antarctica would melt if you put it at the poles. The world today says it isn't so, and when you go back to the other cycles, there wasn't the heat to melt it either. When we remember that this is all probably moot because it's probably not 1 million years old in all likelihood, and that data will change just as it did in Tibet and Greenland. Yes, this means I expect Antarctica and Greenland to remain ice worlds at the tropics for the entire next cycle, when they will go back to the poles and accumulate once again. I'll see you in the morning for the daily update. Be safe, everyone.